Hello, everyone. Thanks for joining us on a Friday. My name is Jess Coonan. I'm the Hudson Estuary Resilience Specialist with New York Sea Grant, located in Kingston, New York. New York Sea Grant is a cooperative program of Cornell University and the State University of New York, and it's one of 34 university-based programs under NOAA's National Sea Grant Program. So today's webinar is the latest installment of the Environmental Justice Mapping Tools project, where our goal is to help support more equitable planning and decision-making by helping communities access local data through online mapping tools that can help visualize disparities and disproportionate impacts. You can access recordings of past webinars that dive into the different mapping tools on the New York Sea Grant YouTube page under a playlist called Environmental Justice. And you can also check out the EJ Mapping Tools Guide. And you can always reach out to me with your mapping or environmental justice related questions. I'll put all that information in the chat once I get through this intro. We will be recording today's webinar and posting it to that same YouTube page. Dr. Reinmann will present for about 40 minutes, and then we should have time for questions at the end. And you can submit your questions throughout the presentation by typing them into the Q&A box. That button is located at the bottom of the webinar window. And the chat feature is also enabled for you to comment and interact with each other and with me during the presentation. And I will put a link to an evaluation survey at the end. We're always happy to hear your feedback. Okay. So here in the Hudson Valley, we're headed into the weekend, bracing for 90-degree temperatures, which can have serious health and financial impacts for those living in urban environments, especially vulnerable populations, such as children, the elderly, those that are pregnant, and those with chronic illness. So in light of all that, we're very fortunate to have Dr. Andrew Reinmann with us today to talk about some of his recent work in Westchester County and share how he uses online tools to access data on tree canopy cover and land surface temperatures that can help identify heat islands and prioritize greening efforts. Dr. Reinmann is an assistant professor at Hunter College at CUNY in the Department of Geography and the Advanced Science Research Center. In addition to some of his latest work studying how temperate forests respond to climate change, Dr. Reinmann devotes much of his time teaching the next generation of scientists. And so with that, I'll hand it over to you.
Great, thank you. All right, let me share my screen here. Okay, is that showing up okay?
Yep, looks good.
Great. Well, thank you so much for the invite. I'm sorry if my face is dirty or I look a little flustered. I'm up in New Hampshire now doing field work, and I literally just got out of the woods just in time for this. So anyway, I apologize if I'm not looking very polished. Thanks so much for inviting me. I'm really excited to have this opportunity to interact with you all and share a little bit about some of the work that we've been doing and provide a little bit of insight for how you might be able to use kind of freely available web-based tools to do some sorts of similar analyses yourself. Okay, first, I want to talk a little bit about, kind of why we care about trees and forests. A lot of this is probably redundant for many of you, but I think it's just a nice way to start. So, of course, trees, forests, those sorts of ecosystems provide a lot of really wonderful ecosystem services related to habitat and biodiversity. They're wonderful for recreation and aesthetics. They can help dampen noise pollution. This is, of course, really important in sort of suburban and urban settings. They're really important in helping to maintain water and air quality. They can play an important role in regulating water flow. And then, of course, in the context of what I'm going to talk about today, they play really important roles in regulating climate, both at global scales and, as I'll show you, at local scales as well. And so we're going to focus on the climate regulation piece and really in the context of environmental justice and in thinking about the places where most people live. I think where trees and forests are really important is sort of how they tie in with the urban heat island effect. And for those of you not familiar, the urban heat island effect is basically a phenomenon where our more developed downtown and even dense suburban areas can be quite a bit warmer than nearby vegetated rural areas. And this is just a schematic here. The difference here they're showing us about 3 degrees Celsius, which is about 5 degrees Fahrenheit. But the magnitude of this varies depending on where you are. For example, in New York City, where I teach, the urban heat island there increases temperatures in the city by anywhere between like 7 and maybe even 10 degrees Fahrenheit at times. So it can be a quite substantial warming effect. And so this exacerbated warming, it can intensify the impacts of heat waves and related public health impacts. In the early 2000s, there was a big heat wave that struck a lot of Europe, and in Paris and other cities in particular, there were high rates of mortality, in part because of the extent to which this urban heat island effect magnifies those negative health impacts of heat. It plays a surprisingly important role in energy consumption in the US. So the urban heat island effect alone accounts, just cooling to offset this, about 5 to 7 degrees Fahrenheit of warming, that accounts for anywhere between 3 and 8% of all of our electricity demand in the country. That's above and beyond what we would pay for cooling for just heat we would experience in rural areas. And it can also exacerbate pollution issues. So in the summer, we sometimes, if you're living in like an urban suburban area, you may hear about these ozone alert days. And ozone is it's a pollutant in the part of the atmosphere where we all live and the air that we breathe. And it's what we call a photochemical reaction, meaning it happens in the presence of light. And it's when we have different chemical compounds in the atmosphere and it's a bright sunny day, and we have high temperatures, the rate of ozone pollution can be really high. And so all of these things related to public health, energy consumption, they all get exacerbated because of the urban heat island effect. And so I find it useful sometimes to just kind of give a very simple overview of what is driving the urban heat island effect? Because for me, it helps me to think a lot about, why are trees important in the communities that we live in? And so here's just like a very simple, not super artistic cartoon I put together in PowerPoint, comparing sort of a fully vegetated forested landscape, like what our natural land covers would be across New York, versus some sort of developed landscape. So when we lose our forest and development goes up in its place. So what's driving this is what happens to sort of the incoming solar radiation that hits the earth, right? And so of course, the amount of sunlight hitting a city is the same as a nearby forest. But what happens to that energy is ultimately what drives the urban heat island effect. And so in cities, we also have a small but measurable amount of heat that's just created from internal combustion engines, or when we turn on our air conditioners and there's heat that gets exhausted. Those sorts of things can contribute in a small way, but a measurable way, to the urban heat island effect. Some of the things that are even more important are things like albedo. So this is related to the color of the surface of the earth and how much light it reflects. So something like snow that's really bright, it's reflecting almost all of the light that hits it. But something dark, like a tar roof or pavement, absorbs a high amount of that incoming solar radiation. And when we replace forests or vegetated land covers, which are relatively light compared to like a tar roof and blacktop, what that means is the less of the light hitting the Earth's surface is getting reflected. So more is getting absorbed. The other thing that happens is vegetation, trees in particular, are really effective at moving water from the soils to the atmosphere through a process we call evapotranspiration. And that process of taking liquid water and turning it into water vapor in the atmosphere, that consumes a lot of heat from the atmosphere and cools the air off. I think like a really nice analogy for this is in the summertime when we start sweating, if we're outside and we're wearing short sleeve shirts and our arms start sweating and you feel a breeze move across your arm, that cooling effect is the evaporation of the water off of your arm. So in a lot of ways, we can think about vegetation and our trees in particular as sort of like the sweat glands of the Earth's surface, then they can be really effective at cooling things off. Of course, when we get rid of that vegetation and replace it with development, there's way less of this movement of water to the atmosphere, so a way lower capacity to cool things off. The next thing that changes is sensible heat and infrared heat. So this is sort of like the air temperature that you can feel, that heat that you can feel. And because of the surfaces that are in a city, it's essentially like a lot of concrete. It can absorb a lot of heat and re-radiate it. There's a lot more of that sensible heat produced in cities compared to a vegetated area. And then when all is said and done, the amount of heat that gets stored in a forest ecosystem and then can get released back to the atmosphere at night is considerably lower when we have forest and other vegetation compared to when we have a city. So it's a combination of how like all of these different dynamics change between a forested landscape and a developed landscape that ultimately make our cities and our developed landscapes much hotter than they would ordinarily be. Just to give you some like visual examples of how this looks, here's a field site that we have in Maryland, and we have this this fancy infrared camera that's looking at this forest on the left. And I like this image because there's no development in it, but it really highlights how even different types of vegetation can have different cooling effects. And so here, basically the greens and blues, those are cooler temperatures. The oranges and the reds, those are hotter temperatures. And so what you can see, of course, is the forest is coolest. You can see this little blotch of red here. And that is, I don't know how well you can see it, but there's this dead tree or snag in the forest. And so you can really clearly see how important not just the tree, but the foliage is in cooling things off. And then we have this grassland in the foreground, and you can see that this mowed path with the short grass is considerably warmer than even the taller grass adjacent to it, which then is warmer than the forest itself. So it's not just development or vegetation. The kind of vegetation can also play a role in how cool a landscape is. To sort of like zoom out a little bit more, I love these sorts of images of New York City. So this is all with satellite imagery that I'll kind of go through later in the presentation. But on the left here is different shades of green that correspond to how much tree canopy covers in any given location. You can see across much of New York, there's not a whole lot of tree canopy cover, but you can very clearly make out the parks, right? Here's Central Park. If you're familiar with New York, here's Van Cortlandt Park in the Bronx. Here's a string of forested parks in Queens, and of course in Staten Island. And when we look at the surface temperature on the right here, and I should point out that surface temperature is the temperature that you would feel if you were to touch the ground. It's not the air temperature, but the spatial variations in surface temperature, which is something that is relatively easy to measure from satellites, does correspond to the spatial variations in air temperature. It's not one-to-one. The surface temperature is often hotter than the air temperature, but it gives us a really good idea for where the hot spots in our cities are and where the cooler spots are. And you can really clearly see where all of the parks in New York City are because they show up as blues, which are much cooler temperatures, right? So here's Central Park, this nice cool oasis in the middle of Manhattan, and you can see how well that corresponds with vegetation. And then this white spot here is the reservoir in Central Park. In northern Manhattan, Inwood Hill Park, a nice dense area of forest also shows up as like this bastion of coolness in the summertime. And so I think this, the landscape scale just shows you how much spatial heterogeneity and heat can really be driven by how much vegetation and trees in particular might be there. But it's not just the heat itself that trees play an important role in. They also can play a really important role in turn what our carbon dioxide emissions are, because that cooling effect also reduces our need for electricity for cooling. And so one sort of bittersweet example of this comes from Worcester, Massachusetts, where in like 2008 or so, there was an outbreak of an invasive insect called the Asian longhorn beetle. And these things will just sort of eat almost every type of hardwood tree. There was an outbreak in Worcester. Here's what this neighborhood looked like before the outbreak. You can see there was a fair bit of canopy cover. the insect comes along, and this is what it looked like afterwards, in part because to quarantine the insect, they had to cut down a lot of the trees. So just to kind of walk back through that, here's what it looked like before, and here's what it looked like after. So there's this huge change in canopy cover, which is horrible. And at the same time, it provided scientists with an opportunity to understand how canopy cover influences temperature and influences electricity demands. And so a group from UMass Amherst studied some of these neighborhoods in Worcester. And so what they found is that in some of these neighborhoods, 2008, before the outbreak, there was nearly 40% tree canopy cover. And on average, the homes here were using about 7.1 kilowatts of electricity per cooling degree day. But after a lot of the canopy cover was lost, canopy cover dropped to less than 10%. And the amount of energy need to cool these homes went up considerably. In fact, it was about a 40% increase in energy consumption during the summer just for cooling. And so this is just a really nice way to highlight that it's not just heat, but it's also like our bottom line, our budgets that get impacted by how we choose to distribute trees. And then that also ties back in, of course, to environmental justice and equity. And so, of course, canopy cover and heat in our communities and in our cities is oftentimes not distributed equitably or evenly. And so I'm just going to highlight a couple of studies that have looked at this in the context of redlining. So if you're not familiar, redlining was a practice by the Homeowners Loan Corporation in the earlier part of the 20th century into the middle part of the 20th century that basically gave neighborhoods a grade for like how kind of like reliable of an investment it was from a mortgage perspective. And if you were given an A, then that was like the best place for a bank to make a loan. If you were given a C or D, those are the places that banks tend to stay away from or just had really high interest rates. And unfortunately, the C's and D's tended to almost always be places where minority and low-income communities were living. And so even though this practice, fortunately, is no longer in place, the legacies of it are very much still with us. So I'll show you a couple of examples of that. So here's some data from Baltimore. They just sort of picked two dates, one in July 2018, August 2017, and they compared the surface temperature. So again, this is like what I just showed you across New York using satellite imagery. Again, just to reiterate, surface temperature is the temperature you would feel. It's not air temperature, but there are these strong correlations between the two. I guess these days in like sort of the pandemic era, we're all very familiar with those little thermometer guns that people point at our head, and what that's doing, it's measuring the surface temperature of our skin. And that's, you know, you can sort of picture a glorified one of those up on a satellite making these measurements of the Earth's surface. So what this work found for Baltimore, for other cities too, it varies across cities, is that even now, right? So this is decades after this practice ended, we can still see the impacts of that, especially when summer temperatures are hotter. So the C's and D's, those are tended to be the lower income communities, most likely to be minority communities. Those are still considerably hotter than the communities that historically were given that A rating. In Yonkers, Groundwork Hudson Valley, this really wonderful nonprofit, did some really great work in Yonkers itself and then across a few cities in the US, also looking at this idea of redlining and what the legacy impacts are. And so here again, we have that A, B, C, and D grading. Again, the A is the highest grade and the D is the lowest. And what they found is across the different cities that they looked at, there's the green bar here is canopy cover. That tree canopy cover declines considerably between those A-graded sites and the D-graded neighborhoods. And surface temperature here in the red increases, right? And so we can start to see this quantitative development of these relationships between tree canopy cover and surface temperature. And so that those hotter environments was often lower income minority communities is in part strongly driven by disparities in canopy cover. Excuse me. And so here's Yonkers, and they put together these really wonderful maps that do a great job articulating this. in the boundaries here, these different colors are the different neighborhoods that were given one of these different grades by the Homeowners Loan Corporation. And the blues, those were the blues and the greens, those were the highest categories. The yellows and the reds, those were the lowest categories. And you can still see, this is recent imagery, the different shades of green are amount of canopy cover. The red areas in particular tend to have much less canopy cover than the blues and the greens. And when we look at temperature, you can also see very clearly, like this one really pops right in the center of the city, that those communities are also still considerably hotter than what have historically been more affluent communities. So even, Yonkers is not huge. Even within these municipalities, you can see a lot of spatial heterogeneity, and it corresponds to these legacy effects of how different communities were essentially treated for decades from a homeowner's loan perspective. Okay, so hopefully that gives you a little bit of a background and a little bit of understanding of these relationships between tree canopy cover and heat in our community. So the next question is, well, how exactly do we map these things, right? And so there are these great solutions that come from satellites that are 2,000 kilometers above the Earth's surface. One of the ones that we use a lot is a satellite called Landsat. Here's sort of a cartoon depiction of that here. And it's essentially snapping pictures of the Earth's surface. And just like with your smartphone, if you were to take a picture with your smartphone and then zoom in, you would see a whole bunch of little pixels. Each one of those pixels from these satellite images, we can get data from. And so for Landsat, it's collecting pixels that are 30 meters on a side, so about 100 feet by 100 feet, which is a pretty high spatial resolution for us to be able to map things like canopy cover and heat. And the satellite is taking images every 16 days throughout the year, and different versions of the satellite have been in orbit for many decades now. So we can even stitch together time series of how these things are changing. And so two of the products that we use a lot based on Landsat, one of them is called the National Land Cover Database, that's put together by a group of different government agencies. NASA, USGS, Forest Service plays a role. And so MRLC, the Multi-Resolution Land Characteristics Consortium, they produce all these wonderful products using that Landsat imagery that can show us at that 30-meter resolution, again, that's 100 feet on the side, land cover types across the country, and also canopy cover across the country. And we'll go into this in a little bit more detail at the end of the talk, but here's an example of what their web interface looks like. And so each one of these colors corresponds to a different land cover type, and there's a legend on the side here. The yellows are usually different types of agriculture. The pinks and reds are different intensities of development. The lighter green is deciduous forest. The darker green is conifer forest. So it's really like this amazing product, really high resolution, does a really good job of characterizing our communities and even the entire country. Another product that we use, also based on Landsat, is something called Climate Engine, which is run by Google, and I'll show you how to use that. But basically, it's sort of like this clearinghouse of sorts in a web interface tool that allows you to zoom in to anywhere in the U.S. or other places in the world as well, and look at different types of remote sensing data. So here in this screenshot, I just have spatial variations in temperature in sort of the lower Hudson Valley of New York. Again, the reds are hotter areas, the blues are cooler areas, and you can see that high amount of heterogeneity. And so we've been doing this work a little bit across the state, but mostly focused on Westchester County with the goal in mind of developing these protocols that can allow sort of anyone to reproduce some of the work that we do using freely available products. And some subset of our analyses can be done even without any expertise in GIS. You can create some of these maps entirely using these web interfaces. So just to give you a little bit of sense of like what some of the data looks like when we do this across New York, we find that the state is about 65% forested. There's about 23% that's some form of agriculture or an old field. 10% of the state is developed. But what's interesting is I'll toggle back and forth again. So again, the greens, different shades of greens, that's forest cover. They have this other really great product that I mentioned called Canopy cover, which is separate from a land cover type. This also takes into account not just the trees in our forest, but the trees in our backyard, the trees along our streets, the scattered trees that may be in a pasture. And that's what this is here. All the different shades of green indicate where there's tree cover. And so what we find from these sorts of analyses is that, yes, forests are really important in controlling how much tree canopy cover is, but so are the trees in our yards and in our communities. In fact, what we find across New York State, oh, sorry, here's just a zoomed in area. I'll show you some statistics in a second. Like I said, we've been doing a lot of this work in Westchester, so I apologize if many of you are not from Southern New York, but some of our maps, that's just where we developed them for. But I think this location in particular does a really good job articulating how important trees in our communities are. Here's what it looks like just for land cover. So pinks and reds are developed areas, green is forest. Now, if we were to look at the canopy cover, we can see it's actually a lot greener than we might expect just from the land cover type alone. And so land cover type is like forest, developed, things like that. Canopy cover doesn't care about the land cover, it just cares about where there's trees. And so you can see pretty big differences there. And it highlights how much power we have in our communities to increase vegetation cover. And across the state, we find that the trees in our yards, in our communities, comprise an additional 0.3 million hectares of tree canopy cover. So that's about another 1 million acres of canopy cover, which is not a small amount. For context, the entirety of the Adirondacks, the largest park in the country, is 6 million acres. So across the state, just the trees in our communities make up close to another 1 million acres of tree canopy cover. And then we can use that sort of information, pair it with maps of temperature. And again, you can start to see these correlations where Central Park, where there's vegetation, that pops out. Water is always cooler, so that pops out. But then once you get into parts of Westchester that are a little bit less developed and have more dense canopy cover, the temperatures are cooler. And this area here, where the Appalachians run through New York, you can see that area is cooler as well. So let me just finish up with just some examples from Westchester County, just to give you an idea of the sorts of things you can do for your communities if you wanted to. So here's sort of a zoomed in land cover map of Westchester, and here's our legend here. And this map is from 2019. Now the data are as recent as this is from 2016. Now the data go up to 2019. But what we find is a little less than half of the county is developed. We can look at changes over time, and we found, apologies that everything is in metric when we do this stuff for science purposes. That's what we're working with. But we've seen about a 26 square kilometer increase in development since 2001. And almost all of that has come at the expense of forest. So the county's nearly half forested, but we're rapidly losing forest cover to development. We can also look at how much of the land area is impervious surfaces like roads and rooftops and things like that. And what we find is a little over 13% of all the land area in the county is a road, parking lot, rooftop, something like that. And then when we take into account not just the trees in the forest, but the trees in our communities, what we find is that 47.3% forested area bumps up to almost 53% canopy cover. We're losing canopy cover across the county as well. But what this indicates is that more than 10% of the total canopy cover in Westchester County is from the trees in our neighborhoods. Again, highlighting how much power we potentially have to change some of the urban heat island conditions and to change the amount of vegetation that exists in our communities. And so here's a map like I've shown you with others. On the left here, it's showing distribution of tree canopy cover. The yellows are areas of low canopy cover. The green is areas of high canopy cover. And here's a map of the surface temperature again. And you can see these same patterns coming to light, right? So here's Yonkers, which is most denuded from a vegetation perspective. It's also the hottest part of the county. And then you can see even in southern Westchester, where just from a broader climate perspective, there's not a lot of differences. We do get a lot of heterogeneity in temperature that seems to be very tightly coupled with where there's tree canopy cover. And so, using these data, what this all kind of starts to come down to is that by increasing canopy cover, we can maybe do a lot to mitigate the local effects of the urban heat island effect, mitigate some of the impacts of climate change, address some social equity issues, depending on the extent to which there's heterogeneity in distribution of canopy cover in our communities. We can also, by reducing temperatures, reduce our need for energy for cooling in the summer. So we can take these data and aggregate it to the scale of each municipality, right? So each municipality is outlined in black here. And so what we did is we took the mean surface temperature of each municipality, we took the total amount of canopy cover, and then we plotted those things together. So each one of these points indicates one of the 40-something municipalities in Westchester. And you see this really, really strong correlation between canopy cover and surface temperature, right? Just like what we can see visually, but now we can actually put numbers on it. And so it's very clear that if we can just keep increasing canopy cover, we will reduce temperatures. And what's, maybe on one hand, maybe a little bit disturbing, but on the other hand, there's some room for optimism here, is if we think about where canopy cover is distributed, what's composing it, we can start to think about where that inequity exists and how we can address it. So what do I mean by that? So on this map here, this darker gray green color, that's where we have forest. The lighter greens indicate where there's tree canopy cover outside of what we would call a forest, right? And so you can see, especially in southern Westchester, there is a lot of vegetation there in places that's not forest. And when we sort of look at this by municipality, so again, each one of these points is a municipality, and we quantify how much of the municipality is covered by forest and how much is covered by just overall tree canopy cover. Of course, we see in areas that have a lot of forest, there's a lot of tree canopy cover. That's not surprising. But as we start to move, as a municipality moves up and away from this blue line, it's indicating that a higher and higher proportion of its totally canopy cover is being mediated by the trees in our communities, along our streets, in our backyards, and not by forest. And so why is that important? Well, our more densely populated areas tend to have less than 20% forest cover, but there's a huge spread in how much tree canopy cover there is, right? It ranges from 10% to almost 60%. Even though all of these communities have very little forest in them, there's a huge discrepancy in how much canopy cover is available. There's been some work that suggests that communities, we should really try and get them to be 40% or more canopy cover to fully realize the benefits of trees. So now if we kind of think about, differentiating our municipalities based on less than 20% forest cover, because that's the area where the trees in our community seem to be most important, and getting to this threshold of 40% canopy cover, we start to see a little bit of a breakdown, and that breakdown is driven by socioeconomics, right? And so what this means is, even though all of these communities have very little forest cover, there's a pretty big difference in what the temperature is. So that change from 20.9 degrees Celsius to 21.7 degrees Celsius, that's probably about a 3-degree Fahrenheit change in temperature-ish, 2 or 3 degrees Fahrenheit. So it's not a small amount. For context, we've seen just from climate change about a 1.5-degree increase in temperature, right? So just this variation in canopy cover at a local scale can have a bigger impact than what we've already seen from climate change. And so I mentioned that there's an equity issue here. So what we find is these areas that have higher forest cover, those are sort of medium income. But in southern Westchester, where you have this huge spread in canopy cover and very little forest cover, there's this huge discrepancy in income, where the higher income communities tend to have much higher canopy cover than the lower income communities, regardless of how much forest cover is there. Okay, so what do we do with this? How do we then think about how to maximize the climate benefits of trees? And so what I always tell people is like, well, first maintain what you have. We're losing canopy cover, we're losing forest cover almost everywhere. And we can maybe start to be creative with thinking about how we can minimize that. For the trees in our communities, what can we do to help to improve and maintain their health? A healthy tree will provide far more ecosystem services than an unhealthy tree. So some of the work that we've been doing on that front is, and with the data sets we've been using, folks can do this pretty much anywhere. We take our map of land cover. We can look at where in the county we're losing the forest the fastest, and it's these areas in the northern part of the county, partially because there's still land there to be developed. But the other thing that we've done is we've taken where there's forest and we've developed just a really, really simple model that helps us kind of like sort of predict areas of forest that might be most likely to be lost to development. And we use just some pretty simple approaches, like we take the parcel size of a property, and if it can be subdivided and it's not protected, all the forests on there we sort of deem as being at the highest risk of getting lost to development. If there's a steep slope, generally that's less developable, and that is in a less dire category. And then places are protected, that's like sort of all of our greens here, those are like the safest category. So when we look at that across, in this case, across Westchester, what we find is that the highest proportion of forest is in this high risk category, right? Where the forest is on land, where the parcel size is large enough to be subdivided and developed. We have a fair bit that's protected or in a low risk category, but still, more than half is in these higher risk categories. So just to give you an example of how this plays out, here's a map just outside of White Plains. The top here, the red is an area that our model suggests as a high risk category. This is what it looked like in 2010. It's all forest. By 2021, you can see that that area got developed. And what's really interesting about this case is that it's pretty much exactly the area delineated by our model that actually got developed. So here's what that looks like now. Here's what it looked like in 2010. Then the sort of thing that we can do is say, okay, well, how did this impact temperature? So we use the Landsat land surface temperature product, and you can see this area in 2010 when it was still forest was quite cool, but just converting it to these condos substantially increased the temperature of that area. Just one more example of that. Here's the village of Pleasantville, where I live in Westchester. And this map is showing changes in surface temperature over this 9-year period, where the bright reds saw the most amount of warming. So I just want to focus in on these two areas. These arrows are pointing to these bright red spots. So this is what it looked like in 2011. And this is what it looks like in 2019. So this bright red spot, that large amount of warming, was just because part of a forest got cleared for development. This red spot down here, there was a little bit of development here, but all the vegetation that was there got cleared for a big condominium complex. So it highlights, even on these relatively small scales, how much the vegetation can matter. Okay, so the last thing I'll end with is like, well, what can we do? I often get asked, what can we do? And I don't always have a great answer, but we've been compiling data across Westchester to look at how different types of policies that a municipality might implement to potentially curb loss of canopy cover, how effective they are. And so take this with a grain of salt, because this is like cursory data and it's not perfect, but it may provide a little bit of insight. So the first thing I always say is like, okay, plant trees wherever you can, make sure that it's the appropriate tree for the location, right? Like don't plant a red oak tree that's going to get really large right next to a power line, because eventually that tree is going to have to come down. So we can, it's not like tree or no tree. We have trees of different sizes and we can plant them. We can find the right tree for the right location. So now in our communities, what we did is we looked at which communities had some sort of a tree ordinance that maybe you needed to get a permit to cut down a tree, which municipalities had some sort of program to incentivize tree planting, and which communities outside of just a tree ordinance you required you to have a permit to take down a tree. And so the red is if there wasn't a program, the green is if there was a program. And so what we found across this 5-year period is that across the board, everybody's losing canopy cover. But the policy that seems like it might be most effective in reducing the rate of canopy loss is having a tree planting program. Every municipality's program is a little bit different, so it's really hard to compare like apples to apples here. But that was the only category of policies that we could pick out as resulting in some sort of significant difference between the communities that have a program and the communities that don't. So just something to keep in mind. Okay, so I always like to end with this slide just because I really like puns, and to thank everybody in my group who has helped out with this work and our funding sources. And then I'll just take the last sort of 5 or 10 minutes here to let me stop sharing my screen for a second. And I will just quickly go through an example on one of these web interfaces for how you might do some of these analyses or make some of these maps yourself. So let's start with I'll go back to just okay. So here's the multi-resolution land characteristic consortium. Here's the first page. I showed a screenshot of it in picture. Here's the website up here. So you can go to this website. This is where you can get data on canopy cover and land cover. And then you can click on tools, and then they have their own viewer. You can download entire data sets if you're savvy with GIS and do all these analyses there. Or if you're not, and you just want to take a look at some of the data sets, you can use their web interface tool called the MRLC NLCD viewer. You just click launch tool, and you get this map of the US. And so you can just pan and then zoom in to wherever you want. So I think Jessica's located in Kingston, so we can go over to the Kingston area and just sort of take a look. So when you open this up, it defaults to these land cover maps. So here's the 2019 CONUS, so contiguous United States land covers. Like I showed you before, the reds are different development categories. You can really zoom in. You can see the type of resolution that we're dealing with here. Each one of these pixels, like I said, is 30 meters on the side, so about 100 feet. And so you can see where there's downtown Kingston, where there's the highest density of development. You can see where there's forest cover and deciduous forest versus coniferous forest. And then the other thing you can look at, so you can just turn these on and off, it'll give you a base layer. You can look at it at different points in time, going back to 2001. So here's what Kingston looked like in 2001. Here's what it looks like now, right? So you can see, if you focus on this area, there's been an intensity in the development, right? From nothing to now. So you can see these things change over time. In addition to land cover, though, you can look at canopy cover. So you just go to this little drop down here, and here's what the canopy cover was in 2016. They come out with these canopy cover products every 5 years. So the 2021 should be coming out within the next year or so. But here you can see the different shades of green are different amounts of canopy cover. And they also have this other nifty tool that is the change in canopy cover between 2011 and 2016. So if I click on that, this is good. This is a nice spot that hasn't seen much. Oh, there we go. So here, the areas in red, those are areas where we've seen a decrease in canopy cover, right? So if we put the 2011 beneath it, there's a decline. You can see a decline over here. And so it's a really simple tool, just at a different spatial scales, to understand how canopy cover is changing and where it's changing. And then you can also, if you made a map and you want to download those data, you can do that. You click on this little open data download tool, And then all you do is you just draw a little box around the area that you're interested in. And then you can come over here and click on the products that you want, and then download the data, and it'll go right to your hard drive, and you can open it up. You can also just take a screenshot if all you're interested in is the map. Okay, so that's the land cover and canopy cover piece. And then the last one that I'll end with is this great little tool called Climate Engine. You have to set up an account through Google. It's totally free, but like all things Google, they make you register. And then, so here's the website, the app.climateengine.com/climate engine. And so what this allows you to do is you can get all sorts of data, but for our purposes here, so you select the type of data, and we'll use remote sensing, and then you have to pick the type of satellite you want data from. For the temperature stuff, we want to use Landsat. And so there's different iterations of Landsat over time, because every few years they launch a new satellite as the one before it either becomes obsolete or to just increase the frequency of measurements. For heat, I'll often use Landsat 5, but you can also just use the compilation of all of them. Then it asks you to pick a variable. There's all different variables that you can use. For temperature, we want to use land surface temperature. If you wanted to look at just distributions of vegetation, you can use one of these two indices. It doesn't tell you the amount of vegetation, but it essentially is giving you a metric of how dense is vegetation or foliage in any given location. That correlates well with things like canopy cover, but isn't exactly the same thing. But so for our purposes here, we'll go to land surface temperature. You have these options of how you would like to compile it. I usually do the mean, and then you can pick a date range. So if you're interested in just like in your community, how is heat distributed? Summer is the most important time for this. So I would always pick the last summer period to last June through August. And then you just click on, you zoom into wherever you want, right? And then you'll click Get Map Layer. It'll take it a minute to process, and then it'll start to populate it. Okay, so for some of these, you'll notice these stripes. And that is just a sensor problem with one of the Landsat satellites, which is why I did this first. And this is one of the reasons why I use Landsat 5, because now if I run it, we should get the data without those stripes. And so you can clearly see where it's hotter. So this is Mechanicsville that we happen to be zooming into. But what's nice about this is that it highlights it doesn't need to be a place like New York City for you to get an urban heat island, right? So here showing you the heat, you can use this little tool to go back and forth, and you can clearly see it's these areas of strip malls and big box stores that are the hottest, right? And the areas where there's vegetation, those are the coolest. If you want to play around with the color ramp, you can do that. So this is what it defaults to, -10 to 45. It does it in Celsius. I think you can change that to Fahrenheit. But for summertime temperatures, I might have it go from, let's say 10, or I don't know, even 20 to 45. And the data itself doesn't change at all. It just changes the color ramp. And then same thing, just like the land cover, there's this download tool. You can select a region, draw a little box around the area, and you can download it. It also gives you this option to just download the PDF of what you're looking at here. So if you're not interested in taking the data and putting it into some sort of GIS framework, and you just want that map for like a presentation or something, you can just download it as a PDF. And again, you can like toggle back and forth here like that. So that's what I have, and I'm happy to take another 10, 15 minutes and try to answer any questions that you all have.
Amazing. Thank you so much, Dr. Reinmann. You covered a lot of ground, no pun intended. And really great the way, we wove together history and how some of your data is showing us these really important thresholds that we can think about when planning. And I also really loved that point that tree planting programs are really effective, something to think about.
Seem to work.
What's that?
I just said they seem to work.
Yeah, especially right now as we're, transitioning our energy in New York State. So we have one question so far. Many homes are converting over to roof-mounted solar panels. Do these show up in heat mapping studies? If so, what is their impact on heat mapping?
That's a great question. I was just having a conversation with a colleague about this yesterday. So I think if you're putting solar on your rooftop, I think like worst case scenario, the heat is going to be no different than your roof because our roofs are typically dark in color. Sometimes the solar panels can be a little bit cooler than we would expect just based on the color because it's actually doing something with the energy that's hitting it. So I think rooftop solar is probably our best approach for deploying solar. We've been thinking about this a lot with I often get emails and ask the question of they want to cut down 30 acres of forest in my community to put solar panels and what do I do? Because it puts us in this weird situation where do I pick renewable energy? Do I pick a forest? And I don't think our options need to be that black and white. And I think to the extent that we can build out rooftop solar, I think that's the best of all worlds.
Great. And do you see big differences between dark colored roofs and light colored roofs?
Yes, huge differences. So just a couple of quick examples. So around 10 years ago, I think New York City had a program where they would subsidize the costs of buildings painting their roofs white. And when you zoom into those areas with this remote sensing imagery and you look at the before and after, it's a huge difference in what the temperature is. And just closer to where I live in Pleasantville, I showed that map of changes in temperature over time. In the bottom corner of that map is another place that turned bright red, meaning a large increase in temperature. And I thought that there was development, but there was no development. But what happened was the building that was there, they changed their roof and they now have a black tar roof, and that greatly increased temperature. So if you have a flat roof, painting it white is a really cheap way to cool things off.
Great. And then can you talk a little bit about the accuracy of this remote sensing data? And, I know there are programs that will kind of use on the ground measurements as well and kind of supplement it. And do they align pretty reasonably?
Yeah, I mean, in the scientific community, people use this land surface temperature data all the time, right? So it's a pretty well established technology. It can be a little tricky to convert land surface temperature to air temperature. That's where it's not always a one-to-one relationship, and you use models to do it, and the models aren't perfect. But if what you're interested in is figuring out where in your community things are hotter, where they're cooler, it's perfect for that, and it will be super accurate in helping you to figure out those locations. And those places that show up as hotter in land surface temperature, those places will also be hotter in air temperature.
Great. We just got another question. Is there some minimum threshold for tree planting to have a significant impact?
Yeah, so there was one paper that came out a couple of years ago based on some work in Madison, Wisconsin, and what they found was that you really needed to get to about 40% canopy cover to maximize the benefits of trees. But we find from a cooling perspective, the benefits to kind of be linear. So if each additional tree that you plant does make that incremental difference. It's not like if you go from 5 to 10% canopy cover, there's not going to be any difference because you still have very little canopy cover. It'll still matter in the places where you've planted them. You may need to get to 40% to have a larger spatial scale impact, but wherever you plant the trees, there's going to be a meaningful impact. Of course, there's a time lag. We plant saplings and it's really once the canopies are more fully developed that you maximize those benefits. But like anything else, we need to think about it as an investment for things 10 years down the line, and just they're trees, you got to be a little bit patient, but any new tree that we plant, as long as we care for it, will pay for itself.
Great. So I'm not seeing any more questions at the moment. So I'm going to take this opportunity to plug an evaluation survey in the chat and just give a huge thanks to Dr. Reinmann for sharing his time with us today. Reminder that this is going to be recorded and posted on the New York Sea Grant YouTube page. And, oh, we got one quick question in just now. Is there an easy way to understand for the layperson a conversion formula for the relationship between tree cover and temperature increase?
For surface temperature, I mean, it probably varies a little bit depending on where in the world you are. I'd be happy to share the equation that we developed for Westchester if folks are just kind of interested in like coming up with just like a cursory estimate for where they are in New York. It's not going to be wildly different, but temperature, I mean, trees aren't the only thing, right? Like if you have a lot of development with white roofs versus black roofs, regardless of how many trees you have, there will be a big difference in temperature. But I'd be happy to share some of the information that we have for Westchester if someone wanted to use it as an exercise to just kind of, get a sense for what it might look like in their community.
Great. And then I just got one last question here. Just saying, and we're getting tons of thanks in the chat, but this analysis is really illuminating. Given the strong correlations, should community members skip the GIS analysis and go straight to pushing for tree policy changes?
Yes.
Right.
I mean, yeah, I think it depends on exactly what information you feel like you need. If you feel like just having a map of a community showing where trees are and where they aren't and where it's hot and where it's cooler, if that's what you feel like you need to sort of develop plans for like where to plant trees, then use the tools that I just showed you, get your maps, have meetings with the community, with the town board, and then I always try to advocate for figuring out ways to allocate as much of a budget as possible to planting trees instead of like doing inventories and things like that. Inventories are important, but there's cheap and sometimes free ways that we can do them ourselves as communities, which can free up resources to planting trees and caring for trees.
Such a great point. And really what this today was all about is making this information more accessible. So thank you again, Dr. Reinmann, and thanks everyone for your questions and your support. And yeah, I'll send some follow-up emails. So everybody have a fantastic weekend.